Jason thing is hilarious. I won't be. It'll be expensive, but
Yeah.
but
Yeah.
she'll be at least two. She just started her first week and she's 10 months old, so she'll be at least two by the time I can bring her down. It will be one.
Well, welcome back, folks. It looks like it's time to get started. Congratulations, we're now on week 7, so already next week is midterm week, but just a reminder, there's no special exam that we're doing on this class on midterm week. Our exam is going to be just the week right after. I don't have any two major announcements other than our quiz number 5 is due on Thursday. We'll have our quiz 6 posted sometime either Wednesday or Thursday morning. And so far, what it looks like for the upcoming exam, it's going to be on this week here, Monday, October 14th. I'm thinking we'll probably go up to chapter 6. I don't think we have enough time to really get chapter 7 completed on this week. And the pattern with how I assign the sections on exams is I try to get everything on here that we covered in its entirety up to this week. That way you'll have a time to do your quiz problem, do your homework problems, get help in office hours, that kind of stuff. That means this week is a little bit weird because on the next week, let's see, we'll be in October. We'll have an ordinary class on Monday, an ordinary class on Wednesday, so we do have to move ahead in the content. We'll probably be finishing off chapter 7 and then getting into a new topic. But then I'll give the same offer that we did on our other exam, number 1. On Thursday of this week, that's going to be, let's see, the 10th. Whatever questions folks have about the upcoming exam 2, I'll be very happy to answer. So we'll just start class off with an informal review on the exam material. And like before, you're welcome to bring anything to class. I'll have plenty of problems posted down here. Excuse me. And you're welcome to bring anything else as well.
When will you post the problem?
Oh, that's a good question. I'm hoping to get stuff here started to be finalized on this weekend. So probably that's going to start happening on the 4th of this week.
On Friday.
Yeah, Friday. Yeah, so this upcoming weekend, starting on Friday, I don't know why I think of Friday as my weekend. It feels like it sometimes. That's when you're going to start seeing material propagate up here. Like we said before, on exam 1, it went up to section 2.5. And so exam 2 is going to start off right here. Exactly. You can get a really good sense of how many questions are coming out of a chapter just based on how much time we spent on it. Chapter 3 was pretty fast for us. Chapter 4, that was another pretty fast one. But chapter 5, we broke down into sections, so you can expect there's probably a little bit more of chapter 5 on this exam. And for chapter 6, probably another short one, kind of like chapters 4 and 5. So we'll have better idea once we get information posted here, which will happen shortly. Other questions about the upcoming exam, folks, or other questions whatsoever?
Chapter 7 will most likely be on exam 3.
I'd say so, yeah. That's the rate we're going so far. We can probably almost plan for it at the moment. Not official just yet, but I think that's where we're ending up.
Today?
I think we're gonna take an extra day on chapter 6, probably Wednesday, is where we're on track for.
Okay.
Other questions at the moment? Okay, and just as I said before, if you haven't gotten your exam one back, don't hesitate to email me or anything like that. If you're not in classes often for or other reasons, then I'm happy to scan your exam and email it back to you. So that's never a bother. Same for any other things like old quizzes and such. I try and look throughout the class and get them handed back before class starts. But if I miss you, I have them down here. You can see me after class or just send me an email. Yeah.
Will we need the scatter plot instructions for the test?
I would say no, that was mostly for homework because a lot of homework problems in my stats lab ask you to produce a scatter plot. And it was more for those kinds of questions there.
I just didn't know, like, make sure we memorize all the, how to get there and how to do everything.
Yeah, no, not so much. There is one thing that we will need. That's going to be the TID4 correlation coefficient setup. That's a mouthful to say, but we'll go over that really carefully once we get to that part in today's lecture.
Is there any way you can redo previous quizzes or not? That is fine.
They are final at the end of the day, but it's still a good idea to come back to them and get extra practice on them. And as far as that goes as well, keep in mind that there's these little extra credit opportunities kind of sprinkled throughout the course, but they don't really kick in until after the final grades are put in. As far as grading goes, it says, or quiz goes, we're going to drop the lowest 2 quiz grades at the end of the semester. So if you had like an off day or an off quiz, something like that, it really is not going to affect you too much. Other questions so far, folks? Okay, well, let's jump back in then. We're in chapter 6. And we're definitely going to need our calculator quite a lot today, so I'll keep that loaded on the sidebar here. But to start out, really, we're going to look at what we were doing here in a little bit more detail and start working towards a brand new statistic. The statistic is going to be called the correlation coefficient. But first, let's read through below about what's all going on here. The trouble with doing a scatter plot like this one here is when we go to explain what we see in the scatter plot, there's like this whole vernacular that goes along with it. Think about histograms. When you put a histogram down on a paper, you have to answer questions along the lines of, what is its shape? Shape has information about unimodal, symmetric, skewed left, skewed right, and so on. And now, same thing with a scatter plot like this one. Based on the cloud of points, we want to analyze the direction it takes, the form it takes, and how strong we think the relationship is just based off what we see. Later on, we're going to quantify this a little bit better by calculating the statistic. So for the moment, it's all just by eyeballs. Any questions at the moment? Okay, so by direction, we mean the pattern as we read left to right. Looks like the points are going downwards, so we would say that this association, the one we were just looking at by the red dot, is negative. So for the form, we're thinking about linear. Can you put a straight line to it versus nonlinear when that's impossible? So this one looks like it has a negative association for the direction. The form is linear. As far as the strength goes, we set it to strong relationship because it didn't look like there's very much spread across this fitting line that we drew on there. So that's essentially what we're trying to do. But one example is definitely not enough because lots of things can happen with a cloud of points. And so that's where we have these screenshots down below. So we have several scatter plots. We'll describe the form, direction, and strength of each plot. And I think I added a point here I should delete. There we go, it's gone. We'll mention any outliers if we see them. And first, well, looking at this one right here, let's go left to right, top to bottom. Would you say the direction on this one is positive or negative? Absolutely. As you go left to right, the points on average seem to be going upwards. So we have a positive relationship. Let's say positive relationship. Now we want to decide on the form. You could say straight. I usually say linear, but it's completely up to you. Would you say that this is a straight relationship or a non-straight relationship? Linear or non-linear? That's a good way to think about it. There seems to be some problems with making it fully linear. For example, if we throw a line through it, this line looks like it does good for a while until the points just veer off on this direction, right? So we might decide, can we fix this line? Let's see, maybe if we go this way. Well, there's still a problem on this. It looks like linear might work, but when you start to break down this line into regions, say from here, these points are mostly above the line. Then from here to here, points are mostly below the line. And finally out here, that's what we want to see, kind of an even mixture of points above and below. It almost looks like no matter what you do with this line, there's a problem. So imagine giving it some curvature. Say this is your line. That one would do a pretty great job. No matter where you're at, the points are spreading above and below. There's no biases. So if that looks like it's the right line to do the job, we would say not linear or not straight. Let's say here, just for our official answer, nonlinear. Not linear or nonlinear, really up to you. I think it's faster to write nonlinear. It's one word now. Does that make sense to folks on the non-linearity of this one? Okay, now this is the tough part. We also want to decide how strong is the relationship. We're doing it just by eye. So if this was a real exam question, I really can't grade this too hard. But just going based off your gut, would you say that this is strong or weak? Or somewhere in the between, you might say moderate relationship. I would kind of agree with you. There is really not too much spread around here. So let's say a strong relationship.
Remind me what the difference is in relationship, the strong and the weak.
A weak relationship could look, say, let me see if I have a good example. Let's put one down here just permanently. A weak relationship might look like this. There's a definite direction to these points, but I'm trying to put down a cloud of points that's just really, really spread out. Sure, maybe a line does a good job describing it, but this would now have a weak relationship, and the further the points spread out around that line, the weaker it gets. So this here would be a weak relationship. There we go. Sometimes the pencil tool lags out. That's really weird. We'll say here, the relationship is strong. Well, we did, folks. That's pretty much what we're doing when we say analyze a scatter plot. We want to say what direction are the points moving in, how are they moving, either a straight line linear or nonlinear like in this, and then just make a quick qualitative assessment of how strong you believe the relationship to be. Again, that's the one I can't really grade too hard because that part in purple, I think that's color purple, really actually requires, sorry, I have to know, yeah, that's purple. That really requires a brand new statistic we'll call the correlation coefficient. So the calculator is going to handle this part very shortly. Any questions, folks, with that first one? Okay, now looking at the second cloud of points right here, I would say this one is the trickiest one in the whole set on example 2. We have several scatter plots. We want to describe the direction, form, and strength, but this is a plot that has no relationship whatsoever. So none of the words that we are describing here actually even apply to this kind of thing. So we'll say on this one that this has no relationship.
Would also be non-linear.
We would not even say nonlinear because once we say linear or nonlinear, we're saying the form of the relationship if it were to have existed. But something like this is the case where there's nothing going on. This looks like just white noise. Imagine if you turned on a TV with a TV turner on, you saw that black and white static. So something like this has no pattern whatsoever. Let's look at it though and see if we really believe that. Would there be a positive or negative relationship? Kind of hard to tell because the points, they're mostly at random heights as you go left and right. A positive relationship should have this. The points must be going upwards. They must be climbing. Or negative means the points have to go down. But this one's kind of just random. Wherever you're at, the points are either low or high. There doesn't seem to be any direction. And as far as linearity goes, well, no, that's a kind of a tough one because there is one line that actually models no relationship. But, sorry, say again? Yeah, good call. So we have an x-axis going this way. We have a y-axis going this way. And the one line that models these data the best would be this. This would be y bar. But if your best way to model your points is just to take the average of y, and that's it, that's a once again indication that there's no relationship going on here. So let's say here, just for the notes, the mean predicts the values of y the best. Now, what would that mean? That means this is a data set with two variables, but they have nothing to do with one each other. If the best way to predict y is just to take the average of y, that's something we could have done in chapter 2. X had no bearing whatsoever on this. And that's another indication that, again, X and Y have nothing to do with each other. There's no relationship between them whatsoever. And there's no way to say that there's an outlier on this unless at some point just went, say, way out here off the map. It's actually pretty regular in its having no actual pattern on there. Well, any questions, folks, so far? Okay, let's go back to something a little bit more normal then. So for this one down below, how about this relationship? First, what would you say the direction is, positive or negative?
Mm-hmm.
Absolutely, as you go from the left to the right, values are going down. That was what was happening in our first problem up here. The horizontal axis was number of grazers of an algae, and as you increase the number of grazers, the growth rate of the algae went down, which makes sense. It should grow less as more and more things are eating it. So over here, we'll say the direction is negative. I'll just say negative direction for short. Next, we can say, how about the relationship? Is this one linear or nonlinear? Absolutely. This one, if you put down a straight line, even if it didn't do a good job at the first try, you could just move the line a little bit and say, well, one of these lines is doing a very good job of modeling the data. Anywhere you're on this line, the points don't seem to be having any pattern of being mostly above or mostly below. So we'll say here, the relationship is linear. So negative direction, linear relationship. And if we said that this one is a strong relationship, would you say this is strong or would you say very strong? Something like that sound about all right? Awesome. Let's go with very strong this time since less spread on this one versus the first case up here. So let's say here, very strong relationship.
You say there's less spread, is that because there's less points from the line itself, or because there's less distance between the points in the line?
I like how you said the second time. It's all about the distance, exactly. So if these points were more like, say, out here in that way, then we'd say the relationship is weak. And if all the points were more, say, like this, just practically right on the line, it just gets stronger and stronger in its relationship.
So if they were more spread out, it'd be like a medium.
Yeah, we might say moderate or medium in strength, something like that. Absolutely. Other questions at the moment? Okay.
If we, sorry, if we were
Oh,
to
no
see that
worries.
the distance between the green dots on the orange line on the very strong relationship were the same distance as the first ones, maybe it's just because there's more dots, it looks like it's closer.
Sorry, I missed that first part. Are you comparing the first two on the left? Yeah, so looking at these,
The spread is more.
it's pretty comparable though. I do agree with you. Any
I don't know
point?
if it looks the same distance, but it's because it's more clustered, but it doesn't look as far apart.
Yeah,
It's as far apart as it is.
it's a pretty tough assessment, right? Because I mean, we're trying to analyze dozens of points. So this one had like twice as many, like you said, versus very little. So any one of these types of descriptions would have been just fine. If someone called this moderate and then this one's strong, I think that'd be about right. But I agree with you that, maybe some of the points have pretty high distances, but not very many on this first plot compared to the second. Other questions at the moment or comments? Okay, well, let's take a look at another one. I think if you really zoom in on that, you could tell that that's a point I added in after the fact, after taking a screenshot. But looking at this, I think everyone would agree it's a positive relationship. Does that sound about right? Awesome. So let's say the relationship is positive, I would say linearity does apply to this, although there is a problem with that point way out there. We're going to call that an outlier in a moment. But this line seems like it would do a pretty good job of modeling the points. Let's see, maybe not the way I drew it though. Look at all these points below versus hardly any above it. If I can't make it seem believable, where there's a balance of points above and below, it might not be linear. But looking at that, I'd say it looks linear, no matter how you kind of move that line around. There's not too many ways to make it seem to be broken. So we will say here, it is linear. And what would folks say for the strength on this one? Again, it's kind of tough to say. Strong as well. Ashlyn's saying very strong with the outlier. I'd say that would be really all great responses. So let's say here, the relationship is very strong. And then I like the other part Ashlyn said, there's definitely also an outlier. This is the one plot where we really should mention it as soon as we spot one. An outlier is kind of tricky because all it has to do is not fit in with the pattern of the data. And I did notice when I was looking into some of the problems in the book, occasionally a point could be out here. And sometimes the book says it's not an outlier simply because if I extend the line through, it is close to that line. So other times the book, without thinking about the line, might call that one an outlier. So there is a little bit of inconsistency in the author's own book. It was written by more than one author. Those little weird issues are never going to affect points in the actual course whenever we come to a real quiz problem or exam problem. But word of warning, it might feel a little inconsistent when you're doing these problems in chapter 6 because of that reason. So we'll say here, there is an outlier. Let me fix my penmanship. That was supposed to be the letter E down there. And the outlier referring to is that one up there. Well, we did it, folks. That's analyzing a scatter plot. Any questions or comments at all with working through these problems? Okay, well, now armed with all this new vernacular, there's lots of things we can do. We're going to try it out with this problem down below. But also, really shortly, we need to define a new statistic called the correlation coefficient, because really the hardest thing about all of this was saying how strong the relationship is. It's really tough. And there's a lot of debate that could go along with this. And also, the units on the axes make a difference too. So we have to worry about lots of different things. Fortunately, once we import the data and crunch the statistics, we'll have a statistic that does, in fact, tell us how strong a relationship really is going to be. So let's put all this into practice on this example here. This is the report, credit card and debit fraud and statistics. So that seems exciting already, probably from the FBI website. Include the data on the accompanying table on the amount of money lost to online fraud for each of the years. This goes from 2001 to 2012, so historical data. So this is money lost in billions of dollars, even though our units don't seem too impressive until we factor in the billions of dollars. In 2001 started off nice, $1.7 billion worth of fraud, but notice there's a pattern to this. Next year was 2.1 billion, 1.9 billion. That might seem like maybe there's nothing going on, but seems to be growing. 2004, 2.6 billion. That was 20 years ago. Wonder what it's like today. Probably close to 10 billion. Who knows? So analyzing the data in this format, it's the same trouble we had with other data sets and earlier in this book. This is just a really tough way to try to see the pattern. It looks like there is a relationship, right? That maybe the numbers are going upwards, but we want to visualize this. We could just go and do an XY plane by hand like we did with some of the problems. We'll go the method of putting this into the calculator to see how it goes. And just a reminder on exams, I'm not going to ask you to produce a scatter plot on an exam. I'll produce it as on the exam itself. This is more for my stats lab when they ask you to produce a scatter plot. This way you don't have to feel like you're just grabbing something by multiple choice based off guesses. That's a lot of staring at points. So first thing we have to do to this, though, this might be slightly annoying, but if you didn't do this last time, you're not going to get the scatter plot. So just a reminder, the way we get a scatter plot going in this class is we have to go to the TI-84 scatter plot instructions. Let me move my window just a bit. Let me run through this just for the folks that might be doing this for the first time. First, turn on your calculator and you have to go to second stat plot. Now, if you've already done this before, this is set up that you don't have to do each and every time. It's a one-time setup. So click on the second key, click on the y equals, this gives you the stat plot, and this should say on. If it's off, click on enter, then just hit enter right here to make sure it's on. And over on the type, go down arrow. If it's set to something weird like the histogram, you need to go back left and select the scatter plot like that. After doing that, your setup is done. Except you do want to double check something else. Any questions first, folks, with this screen? Okay, the other thing you have to double check if your plot isn't coming out right is click the y equals again. They say go to y1 and clear any functions. What they mean is if you see something weird like, say, cosine x, then that's going to mess up the plot in a huge way. So just go up to where that is, hit clear, and you're all set. So everything should be blank here. So that's the one-time setup. After that, this is what you would be doing more routinely each time you're going to get a scatter plot. Any questions first with the calculator? Okay, so back to our data. We're importing the data just in the same kind of way as we have in the past, but first let me fix my window. Hang on, it's doing something weird. Oh, I think I know what's going on. This window's just misbehaving. I'll just get rid of that. Okay, sorry about that. Let's get back on track. So once everything is set up in the calculator, the next thing to do is hit the stat button. This is the thing you would do each time you're trying to do a scatter plot. Go to edit. You definitely want to wipe out everything here. So go up arrow, hit clear with L1 highlighted. It wipes out L1, up arrow and right arrow, and same thing, hit clear and enter. So now L1, L2 are available. We'll just import the data in the usual way. But keep in mind, you have to be really methodical. And although you don't have to go in the right order, the only thing you have to be sure of is when you go to put in 2008, immediately to the right, it has to be 2.8. So we can't scramble the data in that way. So I'll quietly type these in while you put them in, and we'll see if we're getting the same result. One thing that did come up on the exam, by the way, is this is always a little bit awkward. Excel does this too, I believe. When you go to put in a 4.0 in the calculator, it just presents it as a 4. Even if you really try to get in a 4.0, they'll always just put it as a 4. But that won't change your results. That's just something that the calculator does. It gets rid of digits it decides are not needed. Just a few more moments. Okay, anyone need any additional time? Okay, so with L1, L2 all filled out. To get the scatter plot, here's the next thing we'll do. I forget how this goes. Oh, I think I remember. We want to hit the zoom button. This is kind of weird. And you go down to option 9 for zoom stat. So hit zoom or just keypad press option 9, and that's a quick way to get down there. And this is what you should see on your screen. A lot of points going in that kind of direction. Is that what folks are getting so far? Awesome. If I entered in a point differently, then just one of these values is going to budge right, left, up, or down in some direction. But unless I mangled it really badly, everyone's screen should look about the same. So in the homework for chapter 6, a lot of problems say produce a scatter plot. This does just fine. Then look along the list of the correct option, and you'll see what the correct options are. This could save a lot of time actually too. That way you don't have to, again, look at every single point on the plots to decide which one's correct. It should be more about actually creating the plot. So this is really awkward then, because I can't ask a question like this on a quiz or an exam. I really have to produce the scatter plot. So let me put a quick note here and just to convey that. On a quiz or exam, the scatter plot is provided. So you won't see it like this. It'll be just ordinary graphics that you would expect from statistical software. But we did it, folks. Here's our scatter plot. We obviously did it with the TID4 that made it into the screenshot. And because our actual variable right here is in years, this one is also sometimes referred to as a time series plot. Well, let's say here, just to connect those thoughts, year is the explanatory variable. This is a little awkward, and I'm putting this in variable just to be careful, because if we are in, say, chapter 2, we would have called that an identifier variable. It wouldn't be a real variable in that sense, because each year appears exactly once, and its whole purpose is to give you the amount of fraud in billions of dollars. But in this context of a scatter plot like this, we do treat this as if it were a variable. We call it the explanatory variable just to get the plot going in this way. So that's our explanatory variable going this way. Year. Our response variable is the money lost to fraud. There's probably a lot of other variables that could explain why the amount lost to fraud is increasing or decreasing over time. But year on its own seems to be doing a pretty good job of describing how the actual online fraud is changing. So coming back over here, just to convey that on the notes once more, that is the explanatory variable. Or excuse me, the response variable. Sorry for folks working in pen today. Well, Ashlyn is saying, looking at this, we have a positive, nonlinear, weak relationship, or potentially strong. I agree with Ashlyn. That's really kind of hard to put to paper how strong we think the relationship is. Well, looking at this, it says construct the time series plot, which we did. For these data, describe the trend over time, mention the direction, form, and strength, like before. One thing I forgot to put in here, let's put it in here, is just a quick correction. Using the context. Let's highlight that in red since that's a correction after the fact. So going back with what Ashlyn said, this is definitely a positive relationship, since as the years increases, the explanatory variable, which is fraud, also increases. So that's going this way. Fraud. So let's say here, the relationship between year and, I'm abbreviating money lost to online fraud to just simply fraud. is positive. Does that make sense to folks on the positive direction? Okay. Essentially what this is saying is, as the years increase year over year, we expect more and more fraud due to the traffic or due to the credit cards and debit cards. So that's our relationship there. Now for linear, Ashton was saying it's pretty linear. I just can't draw a line on my calculator. So yeah, probably not a good idea, but it's kind of tough to assess on this one, I'd say. If we put a straight line through it to start, let's just assess how well the line does. My straight line could go about like that, maybe. Notice I need to kind of angle it so that when it goes through these clouds of points over here, the points are about above or below. So maybe right around here. We're not trying to make it go through any point exactly. We're trying to make it get as close to every point all at once. Out here on the left, I'm not too sure if it's doing the greatest job. And that's my best attempt at it with a line. I would say these data are pretty borderline at this stage. If you answered this one as linear, I'd probably be happy with that. But let's explore nonlinear as well. If we bend our line just a bit, maybe it could go like this. So there's just a slight amount of curvature to this line. Which one would you say is doing the better job? The straight line linear or the nonlinear bent line? It's okay if you're on the fence on it too. It's kind of tough on these ones.
Second one, you think it's closer to the other ones?
Yeah, I think nonlinear does indeed model the data better on this one situation. But I'm glad we did this problem because it truly is borderline. I try not to bring borderline questions to class. They're going to either obviously be linear or obviously nonlinear. But on this one, let's go with nonlinear for our official response. Let's say here, the relationship is nonlinear. Now, what does that say about the money? Notice there's a follow-up question. Has the amount of money lost to online fraud increased at a steady rate? Linear would have said, yes, it is increasing on a steady rate, but we said nonlinear. That makes that response here a little bit trickier. Let's see what happens when we drew this line. It's increasing pretty linearly out here, but then once we get further and further out, well, it looks like it might be kind of leveling off a little bit. Would you all agree with the way we drew the line? So if that's the case, we can say the fraud grew steadily at first, but tends to level out in the later years. So that's the part right here that's getting bent a little bit down. Let me see if I could draw this even better to try to convey when we said it's leveling out in the later years. So it starts off mostly a straight line relationship, but then it starts to bend down. And I think that's kind of how I was trying to convey it here, getting kind of almost flat in the slope. Well, we answered just about everything here. Let's see, we described the trend over time by mentioning the direction. It's positive. Oh, the form we did mention, nonlinear, but we didn't get to straight. I think that one is still pretty tough on these kinds of questions. Ashland says, if we answered that it could go either way, would that deduct a point? No, I'd be okay with you saying this one is pretty borderline, either linear or nonlinear. That would be an okay response to this one. Well, any volunteers for how strong this one is?
Do you say it becomes less strong over time because it gets farther and farther away?
You can, and that is actually a pretty important analysis. At first, there's very little variability around the line. They're pretty tightly packed. But as you move out, something happened around this year, probably about 2006. Variability increased a lot. Maybe there's countermeasures in the market for credit cards, debit cards that the FBI were looking into, and they were effective some years, that went lower, ineffective other years, it went higher. who knows what happened in the data. So let's go with both of those responses in class and in Zoom. The relationship is strong at first, but as we get closer and closer to 2012, the relationship gets weaker and weaker. So that's a pretty big response on this one, lots of writing. But that's us analyzing a relationship when there's actually context. So those kind of problems usually get a little bit longer to write out.
Could you write the relationship was strong until 2007?
Yeah, that'd be a great way to say it. Absolutely.
And it starts to get weaker.
Absolutely. And again, yeah, that is something kind of remarkable about the data. So I'm really glad people talked about this one. Out here, that looks pretty strong and it looks linear. Something happened in the market for fraud and the countermeasures by either FBI or other agencies. That got weird, again, starting around 2007, became nonlinear. The spread got a little bit more wilder. So analyzing these data is not easy, but it is possible. You just have to work pretty hard on this. In our class, because this is just an introductory statistics class, and regression, which is trying to fit a line to data, is its own subject. We teach a complete statistics class on regression analysis, which is all about that. Our goal is just to introduce the topic. And so going forward in the notes, we're mostly going to avoid this situation when the data is nonlinear. We're trying to model our data just by linear things when we can in this course. But it's good to see the differences between linear and nonlinear to show what is the problem in the first place to analyzing these kinds of data. Well, any last questions or comments at all, folks, with the conclusion here? Okay, well, now we're going to start working towards doing and finally answering the most uncomfortable part of all these questions. The correlation coefficient tells us how strong the relationship is, provided it was linear in the first place. So that's one thing that's a downside. Our correlation coefficient R cannot help us with nonlinear data. But let's start talking about that statistic here. The correlation coefficient R is called just R for short. It's also called Pearson's sample correlation coefficient over a statistician named Pearson. So we just denote that by R and call it correlation for short most often. It's going to measure the strength and the direction of our linear relationship. So tell us if the relationship is weak or very strong, but also tell us if the relationship is a positive one or if it's a negative one. But this is the takeaway though. Correlation coefficient can only gauge a linear relationship, and we have to be very careful of that. It could be used in the wrong context, but the results it gives are pretty much meaningless. Next, it says here, the sign of R matches the direction of the linear relationship. So what we mean here is R is positive when the relationship is positive, and the correlation coefficient is negative when the relationship is negative. So knowing the direction of the relationship tells you the sign of the correlation coefficient R. Notice we haven't said how to calculate it yet. So think of the notes organized in the concepts about the correlation coefficient. And then down below, we'll see how is it calculated, and then we'll actually calculate ourselves. Here's some other key facts to take away though. R is always greater than or equal to -1, and it's always less than or equal to +1. So it's contained within a set from -1 to +1. If you're by, say, the upper limit, that's when you're by +1. That means the relationship is completely strong as it could ever be. All the points lie exactly on the line, in other words, and the line is going in the positive direction. When you get closer to the negative limit, -1, that means your relationship is negative. And the closer and closer you get to -1, the closer and closer all the points get to the line itself. So based off all this, you can kind of paraphrase everything in bullet point 2 here with this graphic down below. This is just a rule of thumb, so keep that in mind when you're using a rule of thumb. In some contexts, having a value for your correlation coefficient out here is not strong enough. Maybe you're working in the sciences where things have to be more exact, maybe dealing with medications. You want the medication to always do what you expect it to do, lower blood pressure, for an example, not have a weak relationship with blood pressure. Other times, a correlation coefficient out here, close to 0, could mean, say, everyone is extremely happy in your office, say this is at work, and maybe everyone's going to go out to vacation because your work office could now suddenly make loads of money. In the stock market, for example, if you find a correlation between industries, and it's a real one, even if it's weak, you can make millions of dollars. It's just that people are going to keep that secret from you. So don't listen to the news for that. By the time you hear stock market information on the news, it's already too late. So all this is context sensitive, but the good thing about this is, again, it tells you your value starts at -1, where it's highly strong, but in the negative direction, or it moves through the weak, back to moderate, to very strong if we're out here, but in the positive direction. So putting all of that together, we'll do one more of these kinds of problems. Here, we just have 4 more random scatter plots are given, no context whatsoever. We'll ask if there's a relationship between x and y, if it's linear, and if it's linear, that means we can talk about the correlation coefficient R. So if we say yes to part B, we'll answer the 2 follow-up questions down below. If we say no to part B, the problem just stops. The data is nonlinear. We won't analyze it further with the correlation coefficient because that's a real requirement. We have to have linear data from the start. So let's give this a try, folks. Oh, on part, I guess this is the first one. Would you say there's a relationship between x and y for these data?
I would say weak linear.
Yeah, it looks like there's going to be a relationship. So let's say on part A, yes, there's a relationship. And for part B, I'd agree. It looks like a linear relationship would work for these data. Let's put down a straight line. Has interesting issues like we mentioned before. Spread is wide out here, but then the spread becomes narrower as we go up the line. But for part B, the line seems to be doing a good job. We'll say yes. So because we said yes to B, we have a linear relationship. Would you call this positive or negative as a linear relationship? Absolutely. The points are trending upwards as we go left to right. So for part C, we'll say positive. And now for part D, we're going to do something that's kind of wild. Well, we can't calculate the correlation coefficient D just yet, but we can say something about it. So on part D, because we said the relationship is positive, on part C right here, the correlation coefficient, which we refer to as R, so that's this part right here, is going to be greater than 0, only because we said positive here. So we have a positive coefficient here. So either use the inequality form, R is greater than 0, or you can just simply say positive. And that would be fine with me as well. What other questions, folks, on our first example here? Okay, I thought that'd be so much fun that we'll just do it again. This one always is a little bit concerning to me because what we're trying to watch out for very strongly is anything that looks like that. It looks like a cloud of points with no definite direction whatsoever. We have no relationship and we can't answer any part of that problem. So let's take a look at this cloud down below. We attempt to put a line through it. Here's what it would look like. Well, I'd say there's a relationship. Would you all agree with that? So let's say on part A, yes, there's a relationship. A line does seem to model these data better. It's not just a cloud of random white noise. So to part A, we say, yes, there is a relationship. On part B, well, would you say linear or nonlinear? I would agree with linear. These are really hard to assess, but we're looking for things to majorly deviate from what we're saying here before we start to say nonlinear. So let's say yes to B. Again, we said the relationship is linear. That means in part C, we have to say the direction. Absolutely, we're going downwards, so negative on that. That takes us to part D. That's where the superstar, the correlation coefficient R, shows up. We want to know, is R positive or negative in this problem? Any volunteers for the sign of R? Absolutely. Essentially, the takeaway of this is whatever you said in part C is your response in part D. So you can just say negative. If you prefer, you can also say R less than 0, but totally up to you how you'd like to format the answer. In fact, let's just let this one be negative for our answer. So those are two problems that worked out pretty well. Let me take these instructions just so we can see them on the next two. So on this one right here, well, I could probably put a line through like this and it does a really good job. But I'd say a lot of people would agree, any line that has some curvature to it, say this one, is probably going to do an even better job. Would you all agree with that, that these are probably nonlinear data? Awesome. So it says, does there appear to be a relationship between X and Y? Would you say yes or no to that part? So folks are saying yay, absolutely, I agree with you. If any line seems to model the points in a certain way, other than the line that's flat, the line that height Y bar, we'll say yes, there is a relationship to it. But now to part B, we drew a curve to model the data better. So when it says, does the relationship appear to be linear, we will say no. So part C is a if so, and part D is based off part C. That means on this problem, we can't answer the next parts. The next parts are asking, would the linear relationship be positive or negative? But we just said it's nonlinear. And part D is asking for the correlation coefficient, but that only qualifies if you said yes on part B. Your relationship had to be linear for correlation coefficient. Well, that one's kind of the odd one out where we couldn't do too much with it. Now looking at this one, doesn't seem like anything super interesting is going on with that one, but let's answer it like before. So on this one, we have that the direction is, or excuse me, that there is a relationship. So we'll say yes to part A. Part B, I think most people would agree. Linear just seems to be doing a pretty good job. Maybe the better one so far. So say in part B, yes to the relationship being negative. So that means we can answer the follow-up questions. Part C wants us to know, or wants us to answer, is this relationship positive or negative? Good call, folks. It's going downwards. So this one is negative. So we'll say here, negative. Then finally for part B, excuse me, part D, we're not going backwards. What would be the sign of the correlation coefficient on this one? Absolutely. If we said negative here, then like Ashlyn said, either say negative or just R less 0. I'll go that way, R less than 0 for the inequality answer on that one. Up to you how you'd like to format the answer. I'm just fine with either way. Well, the whole purpose of this problem is to get a feel for when you can use the correlation coefficient. You have to have data modeled well by straight line relationship. This one, I think you could probably argue with it. This one's kind of borderline, but these ones look like definite linear relationships. And the bigger takeaway is The moment it's nonlinear, we can't use correlation coefficient R at all. So those data have to be analyzed in a different kind of way. Well, finally, we're going to see how to calculate the correlation coefficient. And the answer is we use z-scores, which is kind of cool in a way. We put a little break border right here. So to calculate the correlation coefficient R, you have to do the following. You go to every piece of your data and you standardize them with z-scores for both the x variable, the predictor variable, and the y value, the explanatory variable. So here's the formula for the z-score for all your x data. You take x minus the mean of x, x bar, divide by the standard deviation for the x data, which we call s sub x. These are things you actually see in the calculator here and then. But similarly, to standardize your y variable, you do the same thing, but with your data with y. I just noticed a typo. That should have been a y because these are the y values. Sorry for that typo right there. After you do that process, you have to standardize your data. So that's a lot of number crunching. This is the computation for the correlation coefficient R. You multiply all of your standardized values together, then you add up all the results, divide by n minus 1. That's finally your correlation coefficient R. Weird in a way, right? We'll never do this by hand, so that's the good news. But the bad news is, this is a pretty hard formula to really analyze and say what in the world is going on with it. So let's attempt to do just that. The purpose of the formulas, again, they're meant to give us some intuition on what's going on, even when we use just the calculator to crank these out. Let's grab this to help us out. So here's our candidate where we know we have a linear relationship. That means our methods will work on this thing. Let me just center this real quick. I want to blow this up a little bit more and show what's going on with this part of the formula, the definition rather. So this is a little bit weird, so stop me if things seem to be kind of strange. But here's how I'd start to present this. Notice when you standardize, you're subtracting the mean from your related variables. So I want to put two lines on there. I want a line for y bar. That means you're looking at all the data values as they would be if they fell on the y-axis this way. So imagine there's some weird gravity. The gravity pulls all the points to your left. You want the average of every one of those points. So some weird dot plot now. I would say the average is maybe somewhere around here for the y values. So I'm just going to guesstimate about that height. So that's y bar. Looks like I guessed basically exactly 70. Now, imagine this from the different direction. Imagine all these points fall downwards, making a dot plot like we saw in chapter 2. Where would y'all say the average should be for the x values? Would it be somewhere between 50 and 80? Any good guesses from the class? Maybe more to the left, because as all the points fall down, there's a lot of points coming out to right around here as well. So I think we'd probably be closer to maybe here. Does that sound about right? I'd say about right there for the middle. That's
closer to 50 to 70 than it is 50 to 80.
Yeah, from here to here, it's pretty just about 6 points altogether. But then here to here looks like maybe 12 points coming down. So definite extra weight in that direction. Not trying to put it down perfectly, but looks like it could be somewhere right around here. So this would be the line for X bar now. So when we standardize, we also divide by the standard deviations of Sx and Sy. And what that does is it changes all of these units now. So they're no longer from 30 to 110. These would be values in standard deviations. So think -3 to +3. Same with this axis. So the old numbers you see here no longer qualify to the standardized values. But at this stage, we're finally ready to say, what in the world did this formula do? Because it's really weird. Let's focus on that bit with the yellow highlighting, Zx times Zy. So taking another look at this, recall that when you calculate Zy, that this is the number of standard deviations, that y is away from y bar. So that's what zy measures, and likewise for zx at the same time. Zy can be either positive or negative. If zy is positive, that means your point lies above the mean. If it's negative, that means your point lies below the mean. So let's fill out a table of those values. So zy is positive here. All of your values, when you standardize them, they're above the mean. There's one value in this spot, and it is true that zy is positive here when we standardize. Now go down below, one dot that's odd, zy is less than 0. It's that one right there. It's below the mean, which is at height y bar, represented as the vertical line. And that means when we standardize, this thing is going to come out negative. Barely, it's close to 0. But if we go out here, all of those points have a standardized value that's negative. So we'll say here, zy less than 0. So imagine there's no vertical axis. I'll fix that in a moment. It's all about what's happening to the points for y, whether they're above or below that axis. Does that make sense, what we said on each of those regions? Okay, we're going to do it all over again. Now this time for zx. Same interpretation, and now we're focusing on this line. So if I go over here, then looking at these points, these ones right here, would you say those standardize as positive or negative? Turns out this one would be negative. And the reason is, the line we're looking at this time is for the x-bar line, for zx. These points all lie to the left of their mean, visualized as a vertical line segment this time. So it makes it negative in this region. Zx less than 0. Oh, let me bring the line back though. There we go. So there's a whole bunch of points that have that quality. Then on this one, just one point where zx is actually positive this time, because it lies to the right of this line right here. So continuing on in that pattern, if we're over here, one odd point again, this would have negative value for zx. So zx less than 0. And finally, we're at the last selection of points. Every single one of those points lies to the right of this vertical line bar, x bar. So that means for every one of those, zx is positive. So what have we done? We made a big mess, but notice every one of those things get multiplied together. And once they do that, they get dropped inside right here, and we add them up. Now, what did we say about this problem? We said that the relationship is negative, right? And that implied the correlation coefficient R is also negative. R less than 0, or you could just simply say R is negative. Now, how did it come out negative for these data? Well, take a look at this stuff. You're multiplying zx times zy. You're doing it up here as well. And when you're doing that, you're taking things that are positive, multiplying things that are negative, and you get negative contributions massively in this region. There is 1, 2, 3, 4, 5, 6, 7, 8 points that come out negative when we multiply them together. Again, they all get fed into that formula. Come out here, and there is one positive point when we take zy times zx. That one is just unusual, doesn't contribute very much. Same over here, one positive point. When we multiply a negative times a negative, we get positive. So one positive point. But the moment we come out here, there is a huge smattering. This time, well, not huge. There's more over here in that region. In this region, we have 5 points where the y variable standardizes to negative, the x variable standardizes to positive. So these are negative as well. So we have all these points giving a negative contribution, these points as well giving a negative contribution. That's why the correlation coefficient itself comes out negative. And this is what's happening each and every time we go to calculate a correlation coefficient. We do a standardization, we look at zy and zx, and we just multiply them together. If it's really a negative relationship, then these regions here and here are going to dominate so much that even if you have something that's not fitting the pattern, one positive point, another positive point here, in its overall contribution, it won't make very much difference. So that's what this is all trying to do in the very end. Because these are all standardized values, the units don't even matter. If this was, say, in inches and this was in maybe yards, it would have no bearing if we went from inches to feet, yards to meters, because standardizing removes units as well. These are all in standard deviations. So this is what correlation looks like on paper. How do we actually calculate it? Well, we just go back to the calculator, import our data, like we have right here, and it's not too bad of a computation. We don't have enough time to go into a problem right away, but how about we do, just for the sake of demonstration, the correlation on these data. We'll reset this when we come back on Wednesday, but how's that sound to folks? One last problem? Okay, this is the one-time setup that we need for this last problem. We'll go through this again when we come back on Wednesday. So if you put your calculator away, that's okay. We'll go through this really carefully. So we'll go to this set of notes right here, TI-84 correlation coefficient. This one is a one-time setup. So to make your calculator calculate correlation, it knows how to do it, but it doesn't display the results. You have to do this right here. To view correlation, turn on diagnostic on. That's really vague. So what they mean is, in my calculator, I'm going to hit second and quit. We need to hit the second and catalog button, catalog of all the functions. So second and catalog is, I've lost it. There it is, the number is 0. So on the very bottom left corner of your calculator, hit the second button up here, catalog button down here, and now you have a list of functions. We need to go down to diagnostic on. So press the down button and just wait till the D's come up. C, D. Go to this option that says diagnostic on. When you're on this screen, all you do is you press enter. This shows up on your calculator right after. Hit enter again, and it just says vaguely done. It did something. Essentially, all it did was it turned on the ability to give R at the very outputs down here. So here's how we get the correlation next. After you do that one-time setup, click on, let's see here, the stat key. Then go over to calculate. And we need a specific function. Down arrow until you see linear regression A plus BX. So it's option number 8. So hit enter on that. Now, L1 should always be for X. L2 should always be for Y. If everything looks good there, frequency list should be blank. Store, sorry, say again.
What did you press and calculate?
I went down to, let me see here, stat, calculate. Yeah, option 8, you're right. Yeah, so hit enter there. Then at this menu, you're pretty much just hitting enter a bunch of times. So let me hit it once, twice, 3 times, 4 times, 5 times, and it did it for us, folks. That's a correlation coefficient R for these data if we treated them as linear. No, we said nonlinear, so we really shouldn't use that statistic on these data. Think of this more as a demonstration. Well, any last questions, folks, with how all that goes? Okay, next class on Wednesday, we'll return to this spot of the notes, remind ourselves what we're doing, what the calculator just did right here, and start doing it in real problems down below for these data to start out.
So if we determine that that the data is not linear, we don't need to figure out what R is.
Correct, yes. But you could also assume, because it's an introductory course, for these problems, they're all gonna be linear now, yeah, at this stage. Well, have a great night, folks. See you all in Wednesday's class. Sounds good. Take care.